What that means is there is a bijection between them from G to H. Bijection, remember, meaning injective and surjective, one-to-one and non-duplication. So an exact pairing of the elements between G and H. And this, but not just any old bijection, this has to have a very special property in that it maps the group structure of G across H. Meaning precisely for every pair of elements AB in the domain group G, phi of the product AB is the product of the individual phi values. Okay. So we discussed this definition yesterday. We discussed several examples, both positive and negative, i.e. pairs of groups that were isomorphic, pairs of groups that weren't. And then we more or less came up against theorem 9.6, so I'd just like to take it from there and talk through the proofs of the parts of it. Some parts I've done in the book here, and some parts he leaves as exercises, but I'd like to go through them all. One of your comments on the sheets where we're looking for more solved problems, more solutions. So we'll get into some of that straight away. So theorem 9.6, we see 5 basic properties of the isomorphism relation. First of all, that it's symmetric. So this is on page 156. Theorem 9.6. So we assume phi G to H is an isomorphism. Okay, then we have these statements. Phi inverse, which of course goes from H to G, is also an isomorphism. Yeah? Is there much to prove in that? How do we prove that? Well, he just says in one sentence there, it follows from the fact that phi is a bijection. Okay, well, that addresses the bijection element of it. It doesn't really address the homomorphism. So do we have much to prove here? Probably not a huge amount. But what we do have to prove, you can glean from the definition. Okay. So is phi inverse, which is a map going in the opposite direction, H to G, is this an isomorphism? This will tell us that H is isomorphic to G, which, I mean, we've kind of taken that for granted. Everything I've been saying isomorphism is a relationship amongst groups, and saying that groups are essentially the same. So G is isomorphic to H. Using the fact that H is going to be isomorphic to G. So is phi inverse an isomorphism? Sorry, first of all, is it a bijection? Yeah. Okay. The map is one-to-one and onto, then so is its inverse. Yeah. So we can just say from basic set theory, set mapping theory, phi inverse is also bijective. Okay, but we might want, so we won't go into any more detail on that. But what about the isomorphism property? We want to consider, we need to prove that for every set, I won't call them A and B to confuse them in here, so let's call them X and Y. For every X and Y in H, the phi inverse of the product XY, which is an element over in G, that this is equal to the product of the two elements phi inverse of X times phi inverse of Y.
There's I always forget that dot product in the middle of that, isn't it? The being times between
These two?
Yeah.
Yeah, so this operation that's taking place amongst these two objects is the group operation in G. Yeah?
Yeah.
This operation that's taking place between these two objects, X and Y, is the group operation in H. Yeah. So you have to understand that. So this is what we need to prove. How can we prove that? Well, what we've got is this object here. We've got the homomorphism property for phi. Maybe we can, well, yeah, we'll have to leverage that. It's because of this that the homomorphism property is also true for phi inverse, okay? So this is the points he doesn't address in the book, but it should be fairly straightforward. So we know that for every A, B, and G, phi of the product AB is phi of A times phi of B. Okay. Now what we need to do is make use of the relationship between elements of H and elements of G. They're related via these bijections phi and phi inverse. But we want to talk about a pair of elements in H. This is what we have to prove in the box. We haven't proved it yet. So we let X and Y be elements of H. There are elements A and B and G such that on the one hand, phi inverse of X is A, phi inverse of Y is B, or equivalently, I'm not quite sure which way we're going to use them, maybe we have to use them both ways. Equivalently, phi of A equals X, phi of B equals Y. Yeah? Agreed? And the reason that's true is because the maps are surjective in both directions. So this is true, and the maps are inverses actually. So that's why this is true. Okay, so what are we going to say? On the left-hand side, so we'll start writing this out, or do I need to figure it out? I can say phi inverse of X times Y. That's my left-hand side of the thing I'm trying to prove. So hopefully I can develop it, and end up with the right-hand side. Well, phi inverse of XY is phi inverse X times Y. See, X is phi A, Y is phi B, so that's phi A times phi B. By substitution, from what I know. What should I use next? Can I develop this further using things we know? That's very often the way to push these proofs forward. Just look at possible things you can do to that using the assumptions.
You can just change phi A, phi B to phi AB.
Yeah. Using the homomorphism property for phi. That's the only thing we can do, really. I mean, you can change it back to X times Y again, but I just steps backwards. No progress. So I should use the homomorphism property. So this is phi AB. Phi hom property. And then
Oh, they just cancel because they be.
I get screaming out what to do. It's an inverse function of the original function. Apply an inverse function to a value of the original function, it just gives you back the original value. And phi inverse and phi cancel, as I say, just in very big. And then
We've got substitutions for A and B.
substitutions for A. A is phi inverse of X. B is phi inverse of Y. And that's exactly the thing of the box, the thing I was trying to prove. So I can do it. Yeah, I should have confidence just to launch into a page, but I'm not sure. This might be a bit of trial and error. So it's just a combination of these substitutions and the Hom property for phi. That gives you the Hom property for phi inverse. phi inverse of xy is phi inverse of phi of a times phi of b up above. And that's phi inverse of phi of AB. The homomorphism property for phi. That is phi inverse of, that is just AB. Inverse functions. And that is phi inverse of x, phi inverse of y above. So phi inverse has the homomorphism property. So, and it's, we've already said it's a bijection, it has the homomorphism property, so it is an isomorphism. Okay, any questions about that? You kind of see how when you laid all that, it kind of proves itself, kind of in a way. It wasn't like at one of these intermediate stages, like there's a million different directions we could have gone in. Kind of just look for the possible steps. It seemed to proceed. Statement 2, so at the end of that proof, we know now that H is isomorphic to G. So isomorphism is a symmetric relation. 2 just says the size of G equals the size of H. Well, that really is just proved straight from, since phi a bijection. It's a fact about finite sets that if there is a bijection between them, they therefore have the same number of elements. But for infinite sets, it becomes the definition. The meaning of this statement for infinite sets, size of G equals size of H, is that there is a bijection between them. So for finite sets, the fact that there exists a bijection means they have the same number of elements. For infinite sets, this is the definition of having the same number of elements. Is the existence of a bijection. So since phi is a bijection, the size of G is the size of H. That's for finite sets, it's a consequence of the existence of bijection. For infinite sets, it's the definition of same size. Due to Cantor's theory of infinite sets, he realized that the correct idea for saying two sets have the same size is that there is a bijection. G is abelian, H is abelian. If then. Some people capitalize abelian because they're come after a Norwegian mathematician, Abel, A-B-E-L. But some people don't, because it's used so often, it's kind of lost its capitalization and become its own normal adjective, so people don't capitalize it. Now this I remarked was kind of proved by the argument in the middle of the proof by contradiction of example 9.5. Okay. But let's just do out the argument again. So we can assume G is abelian. We assume the existence of an isomorphism. As I said at the very top of the page, there is an isomorphism phi from G to H. So we just drive forward and prove that H is abelian. So we let H1 and H2 be in H. H1 times H2, this product, we're going to develop this until we see H2 times H1. That will prove it to be until. First step in the argument is So the H1 and H2 are over here. We need to kind of pull it back into G where we know things can switch places. So yeah, so the H1 and H2 come from our images of things in G under the mapping phi. So we need to utilize that back. So that's phi of G1 times phi of G2 for some pair of elements G1 and G2 in G. Since phi is surjective. Okay, that's what we're using there. Everything in the codomain H occurs as a bound. Make sense? Next.
It's 5G1, G2.
5G1, G2. Use the homomorphism property. Prop for phi. Next. G's abelian. 5G2, G1.
It's split them up again. 5G2, 5G1.
The homomorphism property. Here we're looking at phi of product.
Yeah.
Homomorphism property, it's the product of the individual phi's, 5G2, 5G1.
And we can pull it back into the H.
Well, I mean, it's already back in H because 5G2 is in H.
Oh,
But reintroduce the names, the original names, H2 and H1. Yeah, you're right. So the pullback into G really happened into this stage here. Because in these expressions here, the group operation is taking place in G. The element still lives in H because it's an image under phi, but the group action. I shouldn't use the word action because action has a technical meaning, which we'll be seeing later on. The groupy stuff going on here is taking place in G, whereas up here it is taking place in H, and at the end of the argument it's back taking place in H again. And from beginning to end, H1, H2 is always H2, H1. That's saying that it's H is abelian. And there's no restriction on H1 and H2. We didn't use any special properties of them. These could just be any two elements in H. No special properties. Other than that, they lived in H. So again, the fact that there is an isomorphism means the group properties of G transfer across to the same status in H. G, and here's another example straight away. If G is cyclic, then H is cyclic. Okay. Where do we start with this?
It's not going to make any sense because it's on a different page.
So ingredients are going to be, assume G is cyclic. We're going to prove it directly. Think about other ways like proof by contradiction or whatnot later on, but first you should just try a direct proof. It's an if-then. Sorry, if G is cyclic. G is cyclic, then H is cyclic. So we assume G is cyclic, and we're assuming phi G to H, and the all-important homomorphism. And conclusion we want is, therefore, H is cyclic. Then the bottom. Feel how much space you need about this. I mean, it's all about cyclic liquidness, whatever. What does that mean? It's generated by a single element. So we have to roll that out on the page. So that's the point. It's generated by a single element, so we need to name that element. We need to expose it out on the page. Okay? So there is a little g. There is a little g. There is a little g such that g is equal to the subgroup of itself generated by this element. That's the definition. But you need to expose that. Of course, what does that mean in itself? Can you unravel that even? What does it mean? What does it mean to say that G is equal to the secret subgroup generated by G?
G is the set of powers of G, of little g.
Yeah. Exactly. Everything in G is equal to some power of this generator. So that's exactly what we're saying. Some integer n. Right. Now this is good because now we have the notion of being cyclic written entirely in terms of the group operation. None of this shorthand or shorthand, just the word. Okay, it's fully exposed in terms of everything to do with the group operation. Then we have to prove the same thing for H. If we can show that there is a special element in H, such that every other element in H is some power of that special element, the generator, then we'll have shown that H is cyclic.
Is it to say that there exists a y in H, therefore y is equal to, let's say, little h to m, where m and n are the same?
You're moving in the right direction. So you're trying to pounce on the generator of H, aren't you? Okay, this is gun to the head time, right? What is, no, so you've identified the crucial thing. We need to identify, talk about, expose the generator of H. So if we can do that and show us the generator, then we've proved it's cyclic. What is the generator of H?
Say little h, little g. Oh, little g. Yeah.
Well, little g lives over here. You're in the wrong place.
So that'd be 5 little g. You'd have to take something in maths.
Saved your life. Okay, so you wanted to call it a little h, but then you're just kind of inventing a name for it.
Yeah.
We want to discover it from our assumptions.
Mm-hmm.
We want to build it, construct it. Yeah, you get the idea?
Yeah.
From our assumptions. So where might we find the generator of little h? Yeah, you find it by, you take the generator of G and you map it across with phi. If G is so special that it generates G, maybe, hopefully, when you map it across, it also goes to a special element in H. It's going to generate H. So the idea is maybe phi of G, let's call it H, call it H, say, generates H. Maybe. So give ourselves a general, so let's try and prove it now. Let Y be any old element from H. This condition here was what Laura said. This is really what it means to be cyclic. Any element of G is some power of this special generator element. Well, here's any element from H. Can we show that it's some power of this special element, phi of G? That's what we want to say about y. What can we say about y at the beginning?
Oh,
Y is a typical, so 5g is a special thing over here.
y is 5x.
Y is something over there. Yeah, what'd you say?
Y is 5x.
Where's x?
X is an element.
Something over here. Yeah, because phi is surject.
Any.
So we know y is equal to phi of x for some x in G, since phi a bijection. Yeah. Now what do we know? And what can we say?
And x is g to the n.
For which n? Some of us.
Some.
Because we said this, yeah? Every x in G is G, some power of G. Some integer n. Since G is cyclic. Yeah. Now, magic step. Crucial magic step.
Can we split that up somewhere? I don't know.
You do it to a series.
Sorry?
And y.
Phi.
No, and
Don't go applying phi to y. Y is in the codomain of phi. Don't.
it's all right, g. So split it up into n fives of g or x.
It's fine.
One second, I've written something down.
5g of n is a series of 5g's all.
Yeah, okay, so phi, what we've got there, phi of g to the n is phi of g to g.
It's the
N of those.
It's n of that. Which means when mapped, you'd have a series of h's doing the exact same thing.
We've not really got h.
Oh, sorry. Yeah. Sorry.
Well, I think the thing we have to use that is the homomorphism property. And maybe we need to generalize this a little bit. This is the basic homomorphism property for product of two elements.
What if you put two powers?
Sorry?
What if you powers?
Yeah, product of two powers, or more general still, like by induction or by iteration of this. It's like you could say, here's really how to do it concretely. G to the n is g times g to the n minus 1. Yeah. Homomorphism property, this is going to be phi of g to the n minus 1. That's just a straight application of this. A is g, and b is g to the n minus 1. But then you can peel off another g off the n minus 1. G. Phi of g, because you're splitting g to the n minus 1 into g times g to the n minus 2. You can just keep doing this, and eventually what you see is it's phi of g to the n. So actually, I mean, you can instead justify it by a generalization of the homomorphism property. So phi of a to the n is always phi of a to the power n. You just iterate the homomorphism property. Yeah. Just keep on applying it and applying it, peeling off one factor at a time, if you like. Was that what you're trying to get at? I think it sounded kind of like it, but
Adding as opposed to indices, so I had n phi of g. Phi of g.
but that you might have been working with additive notation.
Yeah, that was my problem.
Well, no problem. It's just a different notation setup. Yeah, but here we're operating with multiplicative notation. So yeah, we could say this is 5g, that thing to the power n. This is a generalization of the homomorphism property. If you were to prove it from the ground up, you'd prove it by induction. Yeah. The result when n equals 2, a squared is just the homomorphism property itself, 5A, 5A. And then the inductive step is this counterpart. But of course, what is this? 5G we named as H. This is H to the N. So actually, we took a typical element from H, and lo and behold, it's equal to some power of, typical element of big H, lo and behold, it's equal to this power, some power of this special element of little h, which is 5G. So that shows that H is cyclic, isn't it? Therefore, H is cyclic, generated by anything which is the image of a generator of the G. So again, the group stuff in G gets mapped across to the equivalent stuff in H. Good. Is this fun? This is the most fun I've had all day.
We can tell.
We've had 2 hours of ODEs. We've
This is the only keeping me alive,
actually been mentioned.
Okay, number 5, so that's the end of that proof.
We did do it.
Okay,
We watched in Mala. That's what we did.
If G has a subgroup of order n, then so does H. Remember, isomorphic groups are supposed to be equivalent as groups, the same as groups. So if the sum group property of G, such as having a subgroup of some size, H should have one as well.
That's good. Common notation.
So, I await your construction of this proof. What should we do? Well, we've got to prove it directly. So assume the condition and we'll argue for the conclusion.
Is this a subgroup? Something. A.
What did you say?
We just create, there exists a subgroup of something called
Yeah. What we're assuming is, and crucially, we got to name it. You know, that's once you name it, everything else. Let's call it A. Subgroup of G of order n.
What is that?
No, like
Notation.
gun to everybody's heads.
No.
What is the subgroup of H?
B.
There is. No, you can't name it. There you were trying to do what
5.
Jordan was doing last time.
5.
Yes, 5A. It's the only option. It's the only reason. It's the first thing you grasp a hold of. A is a subgroup of size n over here. We'll just hit it with 5. Then it will transfer over to here.
Of course it has.
Yeah. So we consider phi of A. Everybody's okay with applying a map to a set. Yeah, it's just the set of. It's just the set of images. Well, that's it. Yeah, you just realize, right? The subgroup of H isn't going to come from anywhere else. It's got to come from this one. Okay. So this is certainly a subgroup of H because it consists of images of phi. Number 5 is G to H. Well, we got to prove it's a subgroup. Now we have a subgroup theorem. Let's go all the way back. Basically, we have to prove it's non-empty, prove it's closed under the operation, and prove it contains all the inverses. I'll just get a reference for you. It's subgroups, proposition 3. Proposition 3.13. which is page 47. Actually, this might force us to prove a related rule. So proposition 3.30 gives us three conditions. We have to prove the identity of the group that's present in the subset. We have to prove the subset's closed under the operation, and we have to prove that the subset contains the inverses for all its elements. So we'll need a little lemma in here. I'll write it down as lemma. It might even be one of the lemmas in the chapter. We're spending all our time on this one. This is good, useful stuff. Basically, what does an isomorphism do to the identity element in G? Maps it to the identity. Yeah, it couldn't go to any other element. Remember, groupy stuff goes to groups. So the identity element must map across to the identity. So phi of the identity from G is equal to the identity from H. Okay, nowhere has we haven't proved that yet, so we should just do a quick little proof of it.
Tried to do it and it just instantly hit a brick wall. I was like,
The quick little proof you do is, well, let's take an element H, be a generic element from capital H. Look at phi E of G times H. Yeah, it's actually not so trivial to it. See, you got to think of the little h as being phi of something. Well, it's going to be phi of G, little g, some G. And homomorphism property, this is phi of E of G times G. Well, identity element from the group G, so this is just phi of G, and that's H. So any element H from the subgroup H, when you multiply it by the image of the identity element, it doesn't change it. Therefore, the image of the identity element is the identity element in H. I think you have to do it on the other side, similarly on the other side. You just consider the product the other way around. So phi of EG equals EH. So that's a quick little lemma in the middle of that. But that gives us the first part of proposition 3.30. So the identity from H is an element of phi of A, as the identity from G is an element of A, because A is a subgroup. Second part, so that was the first part of proposition 3.30. The second condition we have to prove is that it's closed under the operation.
always the AB equals something else to the group.
So we have to prove that 5A, remember 5A is our candidate subgroup. 5A, you consider two elements within that. Well, we may as well call them 5A1 and 5A2. That's what two elements of 5A will look like. Good.
Oh, B.
Copy if you want. So this is where A1 and A2 are elements of A. And we have to prove that 5A is closed. So we have to multiply these two elements, and ultimately we want to show that this is an element of 5A. We don't know that yet. But what do we know about that?
By A1, A2, and
Yeah.
brackets.
Apply the homomorphism property. And what do we know about that? Well,
I think we call it the A1, A2 is in J, or in the subgroup.
in A, yeah. A is a subgroup. The product of two elements from it is in the subgroup. So I could write this as phi of A3, where A3 is an element of A, since A is subgroup. Yeah. not just any old subset, it's a subgroup. And this, by definition, is something in 5A, because it's 5 something from A. Actually, I've done this up too much. So that is an element of 5A. So 5A is closed under the operation. If you multiply two elements together of it, you get an element of 5A. 3 contains inverses. Well, for this, you need another little lemma. Useful result to record in general. So what does the lemma say? Talk about inverses. How does an isomorphism interact with inverses?
I was assuming that the image in the image of an element and its inverse both map their relative inverse and
Yeah.
image.
I think what you're trying to say is
5G maps to H, and then 5G minus 1 is mapped to H minus 1.
yeah, it exists. So forget about the H. 5G inverse is the inverse of that element. Yeah? I think that's effectively what you said, but you kind of named 5. You were just introducing another name for those, but you don't need to. So the inverse of an image, 5G, the inverse of that, which is an inverse element over in H, it is the image of the G inverse over here, which is the inverse of that G. Yeah? Well, it's extremely succinct, just the inverse of the root in and out of the argument. Just as our power can move in and out of the argument. This, strictly speaking, what I was talking about here was only positive powers, because I was talking about actual products of elements. But when you combine this with that, suddenly you actually get a much stronger result that this is true for any integer n. Because remember, group elements to negative powers, what do we mean when we say g to the power minus 5?
It's G inverse 5 times.
Exactly, yeah, g inverse to the power of 5. This we understand is 5 copies of this multiplied by 3. That's what's meant by g to the power of minus 5. So with combining with this lemma, this movement of the exponent in and out applies for any integer exponent. So that's our lemma. Does it really need a proof? Well, I suppose it does. So what are we talking about? We're talking about multiplying 5G by this element. Homomorphism property, that's 5GG inverse, which is 5EG, which we've already proved is EH. So therefore, this thing here, that implies that this thing there is the inverse of this thing. Because when you multiply by it, you get the correct that out. So with that little lemma, obviously then if 5A is in A, 5A, that implies A is in A, that implies A inverse is in A, because A is subgroup, it has all its inverses. And that implies 5A inverse is in 5A, but that implies that 5 of A inverse is in 5A by this lemma, micro lemma we just proved. And that, therefore, that is part 3 of proposition 3.30, namely that any element in the subset, its inverse, is also in the subset. Yeah. So 5A has all the necessary inverses. The inverses of all its elements. So by proposition 3.30, phi A is a subgroup. And how many elements does it have? Same amount as that. Because phi is bijection. The number of things in 5A is equal to the number of things in A. So it's by bijection. So having a subgroup of order n over here, the isomorphic image of that group also has a subgroup of order n. And it is exactly the image under the isomorphism of the subgroup over here. Maps across into a subgroup, the same size over there. Okay. So that's the end of theorem 9.6. But many of the other exercises and other results are of that very similar nature, right? Loads of arguments about just exploiting in lots of different ways the homomorphism property and showing how it kind of transfers any group stuff over here from G across to H. Okay? Lots of those similar arguments. Okay, I probably spent more time. I didn't envisage spending the whole time on that, but I think it was very useful and everybody got involved and contributed. It was good. So take those ideas, take what you've learned from that and run with that into the submission problems that I've asked you to do, into the other exercises. And I think I will, so next week we'll deal with the direct products. So I will assign you a bit of reading, just so we can make progress. It's to read through the rest of that section 9.1. So you're just reading through those other theorems on page 157, and Cayley's theorem, 9.12. So we'll discuss that a little bit at the start of next week, and then we'll have our 2 lectures next week on direct products, which is very important construction. But of course, you've been exposed to direct products already when you did your submission problem on, what was it, integers across non-zero reals under multiplication, the set of all ordered pairs. That was your exposure to direct products. And Cayley's theorem you've already been exposed to in one of Jan's problems, when he said that left multiplication by a fixed element is a permutation of the elements of the group. That was one of the submission problems he asked you to do. And that is the key to Cayley's theorem. Cayley's theorem says every group is isomorphic to a group of permutations. So we'll say a few words about that next time. Now, when people first see that, sometimes people think this is a great, or sometimes your reaction to it is that this is a great simplifying result. Because up to now, we're kind of aware there's a whole menagerie of different groups, a variety of different groups. But this says, well, in fact, every group is really equivalent to a group of permutations. So that simplifies everything. All you have to do now is understand groups of permutations, and then you've understood all groups. And that's true in a way, but it isn't that the meaning of it is not to say that, oh, what we previously thought was the complicated world of groups is actually really simple, because it's all just about groups of permutations. Really what it's saying is, maybe what we thought was one simple, small example of groups of permutations, really, even that small, simple, confined class of groups, that's as complicated as all groups. So it's kind of like a fractalness kind of thing. So it's not saying everything is simple because it reduces to this one little family. It's saying the complication of everything is contained in that little family. And groups of permutations are really complicated, because they're every possible rearrangement of a finite set. And the finite set can be any size, so any kind of structure can be replicated with groups of permutations. Okay, but we'll say a bit more about that next week as well.